Swayam Prabha. Digital India. Educated India.
Hi and hello everyone. What we have been seeing was the idea of what is called as open junction network, which, let us recall the description that it is a network of k nodes. External arrivals happens according to a Poisson process, and the service is happening at each node according to an exponential distribution, and there is a routing probability of moving customers moving from one node to the other node, which is denoted by Rij, and there is no limit or on queue capacity at any node. And this is the general idea that you would have seen repeatedly. We are talking about the set network. The setup of the network is what something looks like this. Okay. Then we derived, we stated the global balance equation, and then we gave the solution to that as this in the case of a single server model, right. So, we saw that the network acts as if it is independent environment queue, though really it is not really the case. So, we just verified the solution, and we have obtained the performance measures for this single server at each node open junction network, which is basically will be given by because of the form of distribution, not because of they are MM1 in real sense, but because of the form of distribution that you are getting. So, the Li can be given by rho I by 1 minus rho I, and Wi is by Little's law. Then the expected total number of customers in the network is this, and the expected total weight in the network for any customer before it finally departs is basically W, which is given by this expected total number in the system divided by the total arrival rate to this network or the system, which is basically the Little's formula for the entire network. There are other performance measures which one can define, but let us not worry about that too much. So, this is what is the performance measure that might one. One other performance measure that is sometimes used is the number of visits to a particular node, because there is a feedback and so on. So, how it is anyway, that is one can look at. Okay. Now, what we have seen is open junction network. The restriction that we had was the single server network. Okay. Now, this particular case can be extended to the multi-server case without any difficulty. Okay. This can be generalized to an open junction network where there are, instead of single server at each node, there are CI channels or CI servers at each node. Then again the joint distribution is given by the product of. So, this is nothing but the P at N1, P at N2 and so on, product P at Nk, where now these Pns are really the equilibrium distribution of number in the system in an MMC queue, right, with CI servers here. So, that as you know is given in terms of this with P0, the corresponding P0i, and where this Ai of Ni, just to write it in a simple way, like you use the notation Ai of Ni, which is either equal to n factorial, Ni factorial here, or Ci factorial times Ci to the power Ni minus Ci. That is what would have been the difference in this particular case, as you have seen earlier. And this POI, because it is determined from this condition, that is right. So, it is exactly the same, one can prove it in such generality, but thing is that in the network and the balance equation would be slightly complex up to Ci and so on, that is all, but it is possible that one can show that this is also the case, just like for the single server case, which was very easy to show also. Okay. Again here this open network, you see that this acts as if it is an independent MMCI, just like the previous case, and accordingly the performance measures can be obtained in a similar manner as the original single channel network. Like it will have a only thing, these expressions would vary, right? These expressions would vary, but otherwise this remains the same even if there are Ci servers in each node. That is what would be the case that one can easily generalize to the multi-server case. Okay. So, these are the number in the system. Now, in any queuing system we have also seen the other quantity, which is we have already obtained through his the sojourn times in a way, right. This gives you the sojourn time in the network, this is the sojourn time in the node I, right. We have already obtained the mean performance measures. Now, what about the waiting time distributions that you can think, okay, and related to that is the output processes, okay. Though it is tempting to conclude, because the number in the system result turn out to be the same as MMC Q, the waiting time distribution also would be the same as that of MMC, but that is not really the case, because if you recall when we talked about the waiting time distribution, that is in an MMC or MM1 model, we relied on the fact that okay, Pn, this is not Qn, this is An, okay. So, we relied on this particular fact that the arrival point probabilities were equal to the arbitrary time probabilities of the number in the system, and which further relied on Poisson input. Here, because of feedbacks, right, the arrivals to nodes are not necessarily Poisson in general. Of course, in a series network they will be Poisson, in a again in series network also, like you would see like what would happen to the waiting time when you make more than 2, we will just discuss, but our feed forward network they will be Poisson, but if there is feedback then the input to each node is not a truly Poisson one, okay, and it is very difficult then to talk about waiting time distribution, because the waiting time distribution then will become dependent, right. It is not independent, because suppose if there is a feedback, suppose you assume that there are 2 nodes, first time the customer comes. Now, if you look at the time customer arrives in the system and to the time he will exit the system after getting the service, this will be much like the earlier one, right, for this tagged customer. But suppose if he comes back to this, comes back to again with the feedback, suppose if he comes back again to that node, then what happens, right? Then the time, how long he has to pass through this would obviously depend on his previous time, right, not just on his, but even other customers in front of him, how much they have spent, how long he has been in the first sojourn time, was how long, because when second time when he comes, he would see in front of him some customers who have actually arrived from outside before him, and some customers who would have arrived because of feedback, they are in front of him, or some other customers who arrived from outside after his arrival. He would see both kind of customers, right. Then what happens is that when how long he spent in the first time when in going through the system, so that would determine how many would be these numbers, right. So, there is a dependency, one can easily intuitively also you can visualize that how it will happen. So, they are not going to be independent, things are complex, and because of that, like this waiting time distributions will turn out to be difficult. Not just that, even in a series, right, suppose in this, right, or a feed forward network, suppose if there is if it is not a single server but multiple server, even in a series, there are 2 nodes, assume series, but multiple servers are there, then like what would happen is that, say, the customer who arrives first will get into the service, second customer he will get into the second server, and so on. Once all servers are busy in the node 1, then the other customers would wait, right. But when they go to second node, this sequencing may be broken. Why? Because out of this customer, anyone can complete the service at the earliest, right. So, the customer who arrived later might complete the service earlier with the server, and then he moved ahead of another customer who actually arrived ahead of him in the first node, right. So, there is a bypassing. This also poses problem when you actually want to see how in order to determine the waiting time in this case. So, these are two issues, right, feedback, bypassing. Both these, it has been shown with even very simple examples, I mean as early as in 70s itself, in 1970s itself, like with simple examples, it has been shown that these are not really very simple. Even a very simple situation, this bypassing in case of multi-server systems, feedback in the case of a general Jackson network, these can cause and actually causing complexity problems with trying to determine what is the sojourn time. Okay. So, only for very simple systems or feed forward system with single server, you can really talk in a easier way the question about what is the waiting time distribution, but beyond that things become very complex, because how this behaves, right. As you can see, it is very difficult to gauge, and hence this poses a problem. So, essentially what we are pretty much saying is that nothing much can be said about the waiting time distribution in a concrete way, even in this very simple settings. Now, forget about going beyond this, but mean value still holds because of Little's law. Okay, so, the mean value results are true, they satisfy Little's law, it can be obtained, but if you want the distribution of waiting times, things are not going to be that easy. Okay. One may be also interested about in the output processes in such situations. Okay. Now, as we have seen, for series or feed forward network, the flows between nodes and to the outside world are truly Poisson, but the feedback destroys Poisson flows, and Jackson solution still holds. That is a plus point, but the feedback, there is no Poisson, then you cannot really, if the input itself is not Poisson, then what is going to be the output? It is very difficult to characterize. So, the characterization of this departure process, because that might be of also interest in some situations, is again complex because of feedback. For waiting time, the culprit is feedback and bypassing, but here in the output process, it is really the feedback that is causing trouble. Otherwise, one can characterize in a way what is the output process or the departure process, how it happens. Despite these two drawbacks with respect to waiting time distribution and output processes, this Jackson network is still quite popular and used, because as you have seen, the system size results are quite neat and clean. Though you have a network, you can look at each node individually. Suppose the network satisfies certain properties, then you can look at each nodes individually and you get the corresponding quantities and pull together these quantities to get the system wide or network wide measures that you are looking for. In that sense, this is quite useful, quite neat, clean, and very much useful. Of course, with the assumption that we have this Poisson exponential assumptions, we cannot do away with this in case of Jackson network. So, with that, right. So, this is whether it is computer system or communication system or inventory system, supply networks or production systems, like these are quite useful in determining various quantities of interest in such situations. Okay. So, that is the part about the open junction network that we have seen. Now let us look at a very simple 3 node call center, again taken from the text that you can easily see. What is the description of the system? That is what it is. It's a 3 node, a call center kind of scenario, that calls arrive in a Poisson fashion with a mean rate of 35 per hour at a 3 node telephone system of an insurance company. Imagine an insurance company or some such processes that are happening. Okay. Now, when the call arrives, there are 2 options. Of course, the caller has to press 1 for claims and 2 for policy service. Assume that there are only 2. So, that is what is happening here. So, the caller's listening time, and he makes a decision whether to press 1 or 2, and button pressing time, all these times, if you assume that this is follows an exponential distribution with a mean of 30 seconds. Okay. Now, at this node, like only one call at a time can be processed. So, other calls can wait in the queue, any number of calls can wait in the queue, that is possible. Okay. Now, the data suggests that out of these calls that arrive to this call center, 55% of the calls are related to the claims that is made to the insurance company, and 45% are with regard to policy service, like you need to additionally you want to add certain things and in the policy details or some inquiry or such some requirement. So, this is all is required here. Okay. So, the claim processing node has 3 parallel servers. So, it is a 3 server node, and the service node has 7 parallel servers, both following exponential service time distribution with a mean of 6 minutes, because for claim processing it may take a little bit shorter, because you just have to give out the forms and then tell out which form to fill and close it. And 20 minutes probably takes longer time to inquire what is that, what is the requirement, why do we need, and so on. So, you may whatever it is that. So, just assume that there are 6 and 20 is the number. Now, you assume that all buffers in front of nodes can hold as many calls as come into queues, which means that from node 1 and node 1, suppose if you move to the claims node or service node, that you will wait there for the corresponding expert to answer your call. Okay. Now, you also see that about 2% of customers who after finishing claims, they also go to a policy service, and 1% of the customers who finish the policy service, they also then comes back to claims, right. This is what is the thing that you have. Now, what is your interest? You want to know what is the average queue sizes at in front of each node, at claims, at policy service, right, at node 1, which is out from outside when the call comes. In all these things, what is the average number of queue sizes, or what is the number of total size, system size in those nodes, and what is the total average time a customer spends in the system. So, here queue size means the system, not just the number in the queue, it is number in the system, that is what look at it. What is the total average time a customer spends in the system, right. So, that is what your interest. Now, 1 is for the external arrival node, 2 if you denote the claims node, and 3 as the policy node. So, one can now think about the routing matrix, right, from external, like the routing matrix would then be given by this, right, because in this particular case 55% goes to claims and 45% goes to policy, and after finishing in claims 2% goes to policy, and from after finishing policy service like 1% goes to claims, that is what it is, right. So, this is the routing matrix that you have here. Now, from outside it is 35 per hour, in node 2 and 3 no arrivals, there is a single server because only one call can be there in the beginning in the node 1. So, there is a single server, and 120 is the rate at which call comes, right. So, that is what you have here, right. So, this is what you have processing, because 30 seconds, so 120 per hour you can do. C2, which is claims node, it has 3 servers and 6 minutes, so it is 10 per hour. And here C3 it is 7, so it can handle 3 per hour. Okay. Now, what we have to now get? We have to first get the total mean flow rate, which is basically you have to solve the traffic equation to do that, we have to first compute this inverse, which is turned out to be this matrix. This is the I minus R inverse of this R is given here, that is what is turned out to be here. Then the lambda is basically the total mean flow rate into each node is what given by lambda is gamma times I minus R inverse, which is turning out to be this. So, 35, 19.411 and 16.138 is what you are getting. So, from which, because this is lambdas you got, you have already mu's given, mu 1, mu 2, mu 3. So, you can compute now what is the offer load to each node, which is R 1 is this 0.292, R 2 is 1.941 and R 3 is 5.379 is what then you have. So, obviously, you have 7 server here which is more than this, we have 3 server here which is more than this. So, the stability is there anyway, otherwise that is how you are getting this anyway. Now, using the formula for MMC, you can compute what is LQ1 and LQ2 and LQ3 and also L1, L2, L3, right. So, the total system L is this and the system, the total sojourn time is by the Little's law, it is L by summation of gamma I. So, gamma I is 35. So, this is what you have here, right. So, gamma I is 35 because these two are 0. So, that is what is, that means that is the customer spends about 17 minutes in the network before he leaves the system, that is what you are getting, right. So, basically what you need to do, you need to figure out what are the nodes, how many servers, what are the arrival rates externally, what are the service rates internally and the routing matrix. Once you have figured it out for any network that you can have here, then it is just then the routine calculations that you need to get the performance measures, right. So, other examples would be also similar. Again, basically these are the parameters, that is what you need to determine from whatever description, if at all anything is there, are directly parameters. Fine. Now, this can also be extended in many ways, but we will just see this one extension which is very simple, which is basically when you have multiple customer classes, okay. But here we are assuming that all the customer classes have identical service time distribution and wait in the same FCFS queue. They do not have individual queues, they have the same FCFS queue, that is what we are assuming. Under that, this can be generalized to this multiple server classes, this same idea that you have here. So, what you have then, a customer of one type has a different routing probability matrix than a customer of another type. That was the purpose of multiple class, right. Each one is designate as that. Now, you have to solve the traffic equations separately because each one has a different routing probability matrix. So, you can solve the traffic equation separately for each customer type and then add the resulting lambdas to get the node wise the lambda, which is the node wise mean inflow rate. Now, if R in the superscript T is the routing probability matrix for a customer of type T, which is say suppose assume that there are n type of classes, then you need to solve this equation to get lambda of T, and once you get lambda of T, then you get lambda with these things, right. That is what. Since there is a single queue, you do not need to segregate the server to serve the individual classes because a single queue, and all servers are identical. So, that is that kind of result still holds. So, it is still MMC because of that. So, they have the same average waiting time since they have identical service time distributions and wait in the same FCFS queue. The average waiting time at each node can be obtained via Little's law. And similar is the case with average sojourn time, system wide one. Okay. We can also obtain, in addition to system wide one, the for each customer type at each node also you can obtain the average system size as a proportion of this, right, because this is the ith node tth customer type and this is the overall, right. So, you can take this proportion of this Li would be corresponding to the tth class, right. So, this is also additionally you can obtain in case of multiple customer classes. Okay. So, let us see the same example that we have just talked about the 3 node network of an insurance company's call center. What we have done there is that assume that there are 2% of the calls after finishing the claims process goes to service and 1% from service to claim. But then if you look at it carefully, what we have assumed implicitly is that a customer who has already processed in claims, he can go to service. After finishing the service, again he can come back to claims and go to service and come back to claims and so on. So, he can loop around before he exits, because he might be that 2%, one among the 2% and 1% that we are designating there, right. So, he can revisit the previously visited node, but that is not a realistic in the given scenario. Probably you would have understood that they will not be able to come back to that one once you reach to the service operator, that in person when you are talking to that or when you are getting that. Probably you may have to call again, that is a natural scenario. So, that thing that we had in that implicitly may not be a realistic situation. If that is the case, then what you can do? You can designate these two as 2 different classes. Remember, we have the single queue, FCFS queue for all customers, and the service. Anyone can do service for any of these classes in that node, and then you have the process here, right. That is what you have. So, the way around for this particular situation is that customers who first goes to claims are type 1 customer. So, now what you can do, this node 2, node 3 you can in fact segregate and then with a routing and separately, so that they will exit from there, they will not come back to this here if you do that. So, the nodes itself you are as if designating, one is claims node, one is service node. Actually it is, but then depending upon how the big routing is, things will happen here, right. So, who first go to claims are type 1 customers you designate, and type 2 customers are those who go to policy service for the first. Then the 2 routing matrices for the 2 types of customers, right. So, we are designating depending upon what is where they move first after first node 1. If they go to claims, we call type 1, if they go to service, we call type 2. So, from type 1, right, from type 1 they can go to type 2, right, and then they have to exit from there. They will not be able to, that particular customer who had gone from type 1 to type 2, he will not be allowed to come back to type 1, right. So, that is the case, that is the purpose for which we are designating this. So, that corresponding to that type 1 customers, then the routing matrix would be this, and corresponding to the other one, the routing matrix would be this, right, remember. So, remember the other matrix where here you have 0.55, 0.45, 0.02, here 0.01. Now, what we have happening here, they will go here and from there they will go here and then they will out. From here they will go to service, and from service they will go to claims, and then they will be going out, departing, right. So, since 55% of the arrivals are type 1, so out of 35, so 55% is this much are type 1 arrivals, this much are type 2 arrivals. So, you have computed now for each one, for each class, what is the external arrival rates at type 1. In the other nodes there is no arrival. So, you have these equations. Now, you solve the 2 sets of traffic equations, one for type 1, one for type 2. The 2 types here, 2 classes that you have here. For the first class is this, for the second class is as this, right. So, that is what you will arrange. So, this is basically the throughput for each of this class within each node, that is what you are looking at here, right. Now, once I obtain this, now I have to go node wise. So, I will sum it up, right. I will sum it up these 2 things to get node wise. So, I will get 35, 19.408 and 16.135. Now, you see these 2 values are slightly lower than what was there in the previous case. Go back and see, in the previous case it was 19.411 and 16.138, right. So, and here you see it is 408, it is 135, slightly less. That is because anyway this percentage 1%, 2% is very low. Because of this impact is less, but still you see this little lower total mean flow because of that we are now disconnecting or disallowing the feedback to the previously visited node, right. Because of that, you know, this is slightly lower, okay. And because of that the other quantities also will have slight effect, and that is what finally turning out to be L1, L2, L3, L you can compute the average system sojourn time like earlier you can compute, which is approximately again this was slightly lower here, but it did not make too much impact on this 70 minutes because this is only approximate value. But what you can do now individually, like for each customer type, now I can get the mean number to see like which customer type are more in where and so on. So, that is also possible to obtain in the case of multiple. So, we just use this expression, right, this is a proportion, because this is the total mean flow rate in node I, and this is of the teeth class. Okay. So, the proportion will give you, proportion of this Li would give you the mean number of customers in the system for the teeth class in ith node. That is precisely this, you can obtain it here. Okay. Fine. So, this is all multiple. There are other generalizations that is possible, but things will become complex quickly, and anyway. So, this is what we can cover with respect to open Jackson network. Again Markovian network, but the open Jackson network is what we have covered so far. So, our discussion of this open Jackson network would end here. Okay. Thank you. Bye.